All right, in this tutorial, we'll be talking about a new form of algorithm. So it's tree learning. So most of you will have been kind of pretty familiar with this concept from the lectures, but also just if you've ever written any kind of code, this is a really intuitive idea because it's basically just a big if-else statement. So you can kind of think of it as just a big if-else statement. So let's just jump into question one, just to explain what I mean. So in question one, we're talking about how expressive the trees are. So what that means is, what can they express? So if you remember from previous weeks when we talked about linear classifiers, right? The linear classifier gives you a decision surface that's linear. So the expressiveness of the linear classifier kind of is restricted to just linear decision boundaries. Whereas with trees, we get actually a little bit more flexibility. So if we just start off with the most simple example where we're trying to learn the following function, so A and not B. So this symbol here just means not, which means that if you get an input X, and let's say there's two features, A and B, and each one is a binary feature. So A could either be 0 or 1, and B could either be 0 or 1. Then if A is 1 and B is 1, this should get classified as a false or a negative or whatever you want to call it. Whereas if I get X 1, 0, this should come out as true or plus based on this particular function. Okay, so the way the tree is built is the same way that you would write the if-else statement for this. So the if-else statement would say, if if A is equal to let's call it T to true, then you want to check what B is. If B equals to true, or if B equals to false. So based on what happens to B, you would return false here and true here. And then you would need to also check if A equals to false, then you would just immediately return false. Okay, so this is basically one representation of the decision tree that would kind of model this particular function. Another way to draw decision trees, which is a little bit simpler, at least for me, is to just picture it as an actual tree where you split on the values of the attribute. So for this example, we would first split on A. We would have true or false for A. If you get to this point in the tree, you would just return false. Okay, and if you get to this point of the tree, you need to split on B. B can also take true, false, and depending where you end up, you would get this tree. So these two are the same thing. There's different representations of the same thing. I'll probably use the tree structure because it's slightly easier, and it's kind of more intuitive. And the way you would do prediction is you would get a new input point, X star. You would plug it into the tree. You would follow the path it would take, and then you would get to a leaf node and just return the class at the end of the node. So it's hopefully very intuitive, at this point. All right. If you remember from linear classifiers, I said that there was a function, the XOR function, which basically, if we picture the x1 axis here, the x2 axis here, 0, 1. Okay, so 0 represents false, 1 represents true. Then I basically drew it out, and if you recall, when they're both true, the XOR function returns false. And when they're both false, it also returns false. It only returns true when one of them is true. So you get this this function. And if you remember, I said that this is not linearly separable, which means that a linear classifier cannot directly learn this function, right? Because there's no straight line that I can put between these points that separates the two classes. So we're going to see that decision trees actually can quite easily learn this function, as you can imagine. So let's do that. So XOR A XOR B, or you might see this as XOR with two arguments A, B. So these mean the same thing. Okay, so well, let's just represent it as a tree. I think that's easier. So the first value A gets split into true or false. And then at each of these nodes, we have a continuation where we need to test for the value of B, right? So B gets tested for true, false, and so does B on this side. Now, if you get true, true, that's that's going to be negative, and if you get false, false, that's also going to be negative or 0. And if you get an alteration, so true, false, or false, true, you should get plus, plus. Okay, so just for consistency, let me just put a minus here. So you'll see that I'll switch around between 0, 1, negative 1, plus, minus, positive, negative frequently. So just, and also true, false. So just hopefully that's not too confusing. The reason I do that is because you will actually just run into this notation all the time when you're reading different books or articles. So part of it is me being lazy, but part of it is actually that this stuff kind of comes up regularly with varying notation. Okay, so we can immediately see that the decision trees can actually learn more complex functions than the linear classifier. Okay, so in other words, this tells us that let me just call them DTs are more flexible than the linear classifier. So this statement is kind of true. In 2 weeks' time, I think we'll talk more about linear classifiers and what you can do to augment the data. So with feature selection, which actually gives us more flexible linear classifiers. But just on raw basic algorithm, the decision tree the decision tree is more flexible than the standard linear classifier. Okay, and XOR is a function that can be learned here. So in other words, the decision surface for decision trees is nonlinear, right? All right, and let me do one more example. Oh, actually, one thing before I move on. If you see here what happens, if you see this subtree, actually, sorry, let's move on to the next example, and then I'll come back and talk about that. Okay, so the next example is, so this was B. I'll skip over C and just go to D. Sorry, this was C. I skipped over B. So here we have A and B, or C and D. Okay, so now we have four features or 4 variables. Each one is still binary. Okay, so how would this look? Well, we're still going to have A that's going to be split into 2. And then let's just do the left-hand side first. So if A is true, then we need to check if B is true. Okay. Now, if B is true, then the first part of the statement is true. So you have true or something. Well, it doesn't matter what that something is. You can just immediately go ahead and return true here, right? So if you have A and B, you don't need to check the rest. But if you have B is false, then you rely solely on the second term. So we split on C. Now, if C is true, well, actually first, if C is false, then we can immediately return a negative or a 0 here, because that means that the first condition is false and the second condition is false. But if C is true, then we need to continue on and look at D. If D is true, we can return positive, and if it's not, we return negative. Okay. Now, if A is false, okay, well then the first condition is false, and so we just need to check the second condition. So we split on C, right? So there's no reason to look at B at this point, right? Because there's no value of B that could, give us a different classification, because A and B need to be true. So, okay, so we checked C. Now, if C is false, we can just go ahead and return the minus. And if C is true, we need to check D. And similarly, well, not even similarly, it's identical to the case before. We return this tree. So again, it's really flexible. We can learn difficult logical expressions, and yeah, so this is going to be a nonlinear thing. So you can actually take this guy and try to plot it out, and you'll see that it's also nonlinear. But the interesting thing here is that as we increase the complexity, so we started off with A and not B, then we did A XOR B, and then we did A and B, or C and D. So you can kind of think of this as the complexity. I mean, this is not a very rigorous statement, but you can kind of see that these are getting more and more difficult, right? A and not B is quite simple. A XOR B is a little bit more difficult, and then we're getting more and more difficult. And you can just picture this as, another way to think about this is the code length for the if-else statement is increasing, right? So the first if-else statement has a really short code, right? It's just one statement. XOR needs slightly longer code, and then the third one needs a slightly longer code than that. And you can also see it from the tree. The tree is getting more complex. One thing that happens with decision trees as you increase the complexity of the thing it's trying to learn is that you get replication of subtrees. Replication of subtrees. So you can see that here. We've actually got to learn the same tree twice, right? And the problem with this is that you need more and more data. So, as the tree gets more complex, to actually learn the tree properly, you need to see more and more examples of the data. And the problem with decision trees, I guess, is that as the complexity increases, there's more chance for redundancy. So it actually doesn't use the data in the most efficient way, right? Because you have to learn kind of the same subtree multiple times. So it's got very high expressiveness in terms of how flexible it is, but you also have to watch out for, with that added flexibility, you get a huge cost, which is, potentially redundant use of the data, and just getting these really monstrous trees that are hard to build and quite complex. One thing I'll add here is that one of the big advantages of decision trees is, and you'll see them kind of used frequently in industry, for example, is that they are interpretable. I hope I'm spelling this right, interpretability, in the sense that, if I just give you a big if-else statement, let's say you're doing like, credit decision. So for example, if you're trying to figure out if you should give someone a loan, you can actually just trace their, based on their information. So let's say their age, their, income, things like that. You can actually just trace the decision on the tree and basically pinpoint exactly why the tree made the decision it did. Okay, and that's pretty important in a lot of aspects because, in banking or for credit decisions, for example, you actually need to be able to explain to the person why you are accepting their application or not accepting their application. So for example, had you used a neural network or some other, fancy machine learning model, you would not be able to really pinpoint exactly why the model decided what it did. Okay, so one of the huge advantages of trees is that they're really, really simple to interpret. Okay, so they're extremely popular for use in practice. All right, so I left B out, but hopefully, it's extremely straightforward to go back and do it yourself, but hopefully we get the point, or at least we kind of understand the expressiveness of trees. All right, so that's the first question. So I'm actually going to skip the second question for now. I'll come back to it in a bit. But I just want to look at question 3. Okay, and question 3, the reason I want to look at question 3 now is because it kind of just follows on nicely from question 1, in that, we're given some data. So these are the features, A, B, C are the features, and Y is the class. Okay, so these again are binary features, and you have a binary class. Okay, and we are basically asked to state, so let me write out the question. We learn a decision tree to classify Y given features or attributes A, B, and C. Okay, and we don't do any pruning or anything fancy like that. And then we basically want to know how many mistakes are made. Okay, so this is slightly different to the previous question because now we're kind of assuming that we don't actually observe perfect observations from the true function, right? There's going to be some noise, so that's a more realistic setting. And one way to do this question is just to look at the data points and try to look for inconsistencies. So, for example, if you look at these two, okay, so let's call it, well, this is 1, 2, 3, 4, 5, 6. So x5 is equal to the vector 0, 1, 1, and y5 is equal to 0, x6 is equal to 0, 1, 1, y6 equals to 1. So in other words, we have x5 equals to x6, but y5 is not equal to y6. And so, no matter what you do, the tree is never going to be able to predict either of these correctly, right? It will predict one of them correctly and one of them incorrectly every time, right? So what would this look like? Well, actually, before I draw the tree out, there's another example here. Not that one, this one. Okay, again, you have the same values for all the features, but you have a different class. Okay, so basically this tree, whatever tree we're going to learn on this is going to make 10 out of 12 correct classifications, but it's always going to make errors on at least 2 of them. Okay, now let's I guess we can try to draw this guy. Well, okay. So we have three features, A, B, C. Maybe I won't draw the whole thing out, but I'll just start off until we get to the first inconsistency. Okay, so A can be either 0, well, let me just call them true or false. Okay, when A is false, we look at B, and so we also split on true, false. And then we also then need to split on C. Okay, so the way you'd build this in practice is you look at the first example, right? You have 0, 0, 0, so false, 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 and then you should return 0 here. Okay. For the second example, you'd have 0, 0, 1, right? So false, false, 1, and then you should also return 0. Okay, in other words, you could actually get rid of this, well, assuming you didn't get assuming you didn't get the same input with a different output, if this was your final tree, you could get rid of this and just replace it with a 0 here. Okay, to simplify the tree. But let's just assume you keep everything. Okay, then we move on to the third example. So 0, 0, 1, false, false, true, 0. Okay, we already did that one. 0, 1, 0. So false, true, false, and that has a class 0. And then we come to this inconsistent one. So 0, 1, 1. So that's false, true, true. And the first example tells us that we should put this as 0. But the second example tells us that we should put this as a 1. Okay, these are x5 and x6. And so basically, the final tree has to just pick one of these randomly. And so it is going to make an error on one of them. Okay, but the basic idea here is that this is how you kind of build the tree based on this simple example. As data comes in, you add nodes, you add conditions for each of the nodes, and then the leaf node is kind of the class that you return. Okay, but with noisy data, you can actually get misclassifications. All right. Hopefully that's pretty straightforward as well. Okay, and before I go to question 2, let's just look at question 4 quickly as well. We've looked at we've looked at binary classification when the class only has two possible values, true, false. But you can actually just very easily do multi-class classification. So, in other words, you would have your tree be split into maybe 3 nodes. 0, 1, 2, for example, for a feature with 3 values, you would have 3 splits instead of 2. But you could also just return one of k classes, right, quite easily. So this could be any value. This could be, A, B, C. In other words, the tree can return any possible, value of the actual class. So the question is kind of saying, if you have k classes and you want to learn a tree, what is the maximum training set error? Okay, so if you have, let's just kind of picture the data set. Let's call it S, and let's say you have k classes. So what is the kind of the worst possible case for your tree? Well, imagine that you had, let's split the data into 1, 2, k minus 1, k. So imagine like this is the data in class 1, class 2, and you have k possible classes. The worst possible thing that could happen is that, imagine that you have 1 over k of the data, so just a uniform split in each category. Okay, then, so again, we're looking at the maximum. Okay, so I'm trying to picture the worst possible case. So this is not, obviously, you could build a model that's better if you have features, but here I'm looking at like, what is the worst thing that could happen? Well, the worst thing that could happen is there's an equal split of the data across the k classes. And I guess like when you look at arbitrary data here, we don't have any features, so we can't really do anything. We just basically have to work with, so what I mean is that you actually don't have features in this example. You just have an output, y. And let's say like, these are your observations, okay? And you just have an equal split in each class. Okay, so you can just picture, so there's no features. We can't actually do anything with the features. We can't do any splitting or anything like that. So what can you do in this case? Well, the best thing you can do is just have your decision tree return one of the classes. Right, so just pick any class arbitrarily, say class 1. So every time you get a new data point, you just predict 1. Okay, that's kind of the best thing you can do in this scenario because there's really nothing else you could do. You don't have features to give you more information. Okay, so what would be the error in that case? Okay, well, if you're always predicting, what would be the error on the training set? Well, if you're always predicting 1, then you are going to get 1 out of k correct, right? So 1 out of k correct classifications. But then you're going to get the rest, right? These ones are going to be wrong. So you're going to get 1 minus 1 over k, which is just 1 minus k over k, incorrect. Okay, so the idea is that yeah, so this is the best you could do. So the maximum error that you can achieve is 1 minus k over k. Okay. So this is in the worst case for the data. If the data was not uniform, was not split uniformly, then if you stuck to this rule where the dt returns 1, and let's say it's the majority clause, then it would predict some number m bigger than 1 over k correct, right? Because if you now have a split of the data, let's say in class 1, for example, you actually have more than 1 over k, right? Then predicting the majority class is going to give you an error it's going to give you a number of correct classifications that's bigger than 1 over k, and so the training error is going to be less than this number. Okay, so the worst possible performance is just when you have the uniform split of the data. Okay, and so this kind of takes us into the idea of entropy, which is extremely important for actually building decision trees. Okay, so what is entropy? So I just really wanted to hit home the fact here that like the worst possible performance of the decision tree happens when there's uniform split of the classes. Okay, so that's kind of like the most uncertainty. It's almost like you have to guess. Well, you do exactly have to guess So entropy is kind of trying to quantify that. So the way you'll kind of see it defined is that it's a measure, measures homogeneity of the samples. But you can also think of it as measuring the uncertainty or the spread of probabilities. So any number of ways to think about it, but basically it's kind of measuring how uncertain things are. So in the example we had here, if you have a uniform split, right, then the uncertainty is maximized, right? Because you basically have to, it's just a random assignment into k classes, right? Whereas if you had all of them in one class and none in the other classes, then that's kind of the that's completely certain, right? Because there's no randomness in that. Okay, so this entropy is a way of measuring the uncertainty. And basically, if we have a set S of well, let's just look at the two class case. So positive, negative examples. Then we want to measure the uncertainty. We'd look at the entropy in the sample S, and I'll usually write this as H of S is equal to the following. Okay, where P plus is the proportion of positives, and P minus is the proportion. So S has a certain number of positive and negatives. This is just the proportion. So P plus is the proportion of positives times the log of the proportion minus P minus the log of the proportion in the negative class. So the log here, it doesn't really matter what base you take it to, but usually we'll take it to the base 2 because then the entropy is going to be in bits. Okay, and in information theory and a lot of learning theory, it's more convenient to talk about bits, but it actually makes no difference, mathematically speaking, if you take this to be log base 10 or log base e, it makes no difference. All right, so this definition works for two classes, but it also just works for general. So general classes. So if we have a k-class problem, so multi-class problem, then the entropy of the sample is just the negative sum pi log pi, where I is just going from 1 to k. Okay, so basically you can see that when k equals 2, you just get the definition up here, but it just works in general for any class problem. Okay, if entropy increases, then uncertainty also increases. Okay, so these two are kind of measuring the same thing. So what do I mean by that? I mean that if you have a sample, here's your S, and we're just looking at the two-class sample, then if half of them are positive and half of them are negative, this is the maximum uncertainty because basically the data is perfectly split. The best thing you can do is just randomly guess 50-50 of the time. If you have another sample, so let's call it S1, S2, let's say you have this split, so 25% positive, 75% negative, then the uncertainty is slightly lower, right? Because there's kind of less randomness in the data set, and So you should expect that the entropy of S1 to be greater than the entropy of S2. So this is kind of how I think about it. And let's actually just look at a more general definition. So in statistics, if X is a random variable let's say it's a discrete random variable. So a discrete random variable that takes on, so let's say X can be can be equal to 1 to up to K with probability probability X equals to Xi equals to Pi. Okay, so in other words, I'm just giving you a distribution for a discrete random variable. The discrete random variable can take any value 1 to K, and it takes on that value with probability Pi. Okay, then we say that you can actually find the entropy h of X using the same formula. So minus the sum I equals 1 to K, probability X equals to, so I used I here, but really it's just X equals to I, log of the probability X equals to I. Okay, and just to simplify the notation, this would just be I equals 1 to K, Pi log Pi. Okay, and if you notice, if you recall how we defined expectations in general, right? So if I look at the expectation of some function of a random variable, discrete random variable, if you remember, we sum over all the values that the random variable can take. Okay, it could be finite, it could be infinite. I'm just looking at the finite case at the moment. And then we multiply the function g of I by the probability that X equals to I, right? This is the formula for expectation. So if you look at this guy over here, this is just the expectation of the negative of the log Px, right? Because what is the expectation? It's checking out this function for every possible value of X multiplied by the probability that X takes that value, right? Multiplied by this probability. So the entropy of a random variable is just the expectation of the negative log probability of the random variable. Okay, you don't need to worry too much about it, but I think it's interesting to see this because entropy comes up a lot in statistics as well. So let's just do an example just for concreteness. If X is a Bernoulli distribution with parameter P, then we know that X can be either 0 or 1, right? And the entropy of X is going to be minus, well, okay, it takes 0 with probability 1 minus P, and it takes value 1 with probability P, right? So it's going to be minus 1 minus P log 1 minus P, right? So this is probability X equals to 0 times the log of probability of X equals to 0 times the negative. And then we need to take care of the other probability, which is P log P. So this is minus probability X equals to 1 log probability X equals to 1. So this is all possible values for X, right? 0 or 1. And so this is called the the entropy of the of the Bernoulli random variable. Okay, so what? So let's actually just let's see. Let's plot this thing. I'm just going to use my grapher here. So I have minus x log x minus 1 minus x log 1 minus x. So basically I'm just plotting the entropy as a function of p, right? So what I want to show you is that as we change the parameter p, right, the probability of a success, we get different values for the entropy. And I want to basically plot for different values of p, what is the entropy, right? Okay, and it just looks like this. So it's just a parabola, and it takes values 0 to 1. Okay, so obviously p can only be 0 to 1, and the entropy is maximized somewhere in the middle. It looks like it's maximized at 0.5. In other words, it's saying that the maximum uncertainty of the let me draw it here. The maximum uncertainty of the Bernoulli random variable happens when the p, the probability parameter, is equal to 0.5. So in other words, if you're doing a coin toss, a fair coin is the most uncertainty, right? Because it's kind of the most random possible thing. All right, so let's just kind of verify that it is maximized at half. So how would we verify that? We would differentiate the entropy with respect to p, and we would set it equal to 0, right? So maybe I'll leave this as an exercise, but you will show that this is actually maximized at p equals to a half. Okay, and it should kind of make sense because, you know, at either extremes, the entropy is measuring uncertainty, right? So if p is equal to 0, okay, that means that if you're doing these coin tosses, you're always going to get a heads, and so there's really no uncertainty, right? So there is 0 entropy. But if it's a fair coin toss, whether you're going to get a head or tail, the randomness there is maximized. Okay, so we'll usually be using entropy in this course to look at samples of data, but you can also look at entropy of probability distributions, right? So for every distribution, for every different p, I'll get a different probability distribution for the Bernoulli random variable, and for each of those distributions, I can get a value for the entropy. Okay, let me also just for completeness show you another example for continuous values. So if x is a continuous distribution, then h of x. So if you look at the previous slide, we defined, you know, we can look at the entropy as the expectation of the negative of log px. So we can actually just use that definition for the continuous. So negative expectation log px. Except that this px now is a density function, it's not a mass function. So you can look at the supplementary video for tutorial 1 if you're confused by this. But let's look at a specific example where we have a normal random variable with mean mu and variance sigma squared, and you're looking at the, so just to remind you, let me use p to denote the density. This is 1 over root 2 pi sigma squared. Okay, so this is the density function for a random normal variable. And x can be any real number, right? So this is a distribution on the real line, which is centered at mu, and the width, right, is determined by the standard deviation sigma. Okay, and just to make life a little bit easier, I'm going to write this as 2 pi sigma squared, negative 1 over 2 e negative 1 over 2 sigma squared, x minus mu sigma, x minus mu squared. All right, so now we want to look at the entropy, which is the negative of the expectation of log p of x. So what does expectation actually mean, right? Expectation, if you look at this here, expectation is the kind of the weighted average of the function, and the weights are the probabilities. when you have a continuous distribution, you can't sum over all the possible values. We actually do, we integrate. So think of the integral as an infinite sum, right? That's what an integral is, of the function log px times p of x dx. So this is the integral. This is just like before, the sum of g of x p of x, right? Except now we're looking at the continuous realm. So we have the integral, and we need to look at the dx, which is the variable that we're integrating with respect to. Okay, let me simplify this a little bit. What is the log of p of x? Well, p of x is up here, right? So if I take the log, what's going to happen is that the negative half will come down. And so I'll get negative half log 2 pi sigma squared. And then if I take the log of, so log of AB, right, is equal to log A plus log B. Okay, and by the way, here, just to be super clear, I'm taking the log with base E. Okay. But this rule holds for any log. And okay, so this is multiplied by this. So when I take the logarithm, I'll get the log of this part plus the log of this part, and the log E 1/2 sigma squared x minus mu squared times p of x dx. And then, okay, so you should hopefully see that if you take the log of E with the same base E, right, these just cancel out. So what I'll get is negative half okay. Now let's just do some simplification. Let's expand the brackets and take the negative outside. So we'll get two integrals. Well, for the first one, actually, we can just take everything here outside, right? Because there's no x in that expression. But we still have this p of x term. And then for the second integral, we end up with 1/2 sigma squared integral of x minus mu squared p of x d of x. Now look, you can't take this part out, right? Because this x is the variable that we're integrating with respect to, so you can't actually remove it. Whereas here, you've got no expression for x. Now hopefully it's easy to see. This integral here, right, must be equal to 1, right? Because if I have a distribution, the integral over the entire real line of the density is just basically summing up all the area underneath. And so because it's a probability distribution, it has to add up to 1, or it has to integrate to 1. Okay. And the second thing you should notice is that this expression here, the second integral, is just the expectation of x minus mu squared, right? What is an expectation? You integrate the function weighted by the probability dx, right? So these two are the same. And hopefully you can notice that this is basically just the distance of x to the mean squared, right? So the squared distance. So the expected squared distance, right, is just the variance of x. And the variance of x in this particular example, right, is just sigma squared. All right, so what we get is let me just fit it down here. We get 1/2 log 2 pi sigma squared plus, and from this expression we're just going to get sigma squared. Okay, and then finally simplifying it a little bit, we get, so these sigma squareds cancel out. We've got 1 over 2 log 2 pi sigma squared plus 1. Okay, so let me maybe open up a new page. Okay, so we just showed that for x normal mu sigma squared, right, the entropy of x is half 1 plus log 2 pi sigma squared. So, okay, that's fine. We just did the, the integration. The calculus is not too difficult. But the important thing is to understand kind of what this actually tells us. It's telling us that the uncertainty increases, right? This is a function of the variance, sigma squared. So as you increase sigma squared, right, this term is going to increase, and so the entropy also increases. Well, let's kind of make sense of that, because what does a normal distribution look like? So normal distribution looks like this. Let's say this is for sigma squared equals to 1. But what happens when you increase the variance of the normal distribution? So if we keep the mean the same, but then we increase the variance to, say, 4, what happens basically is that the normal distribution gets kind of fatter, right? Fatter tails. It will still be centered at the same place, but it will be like much more spread out. Okay, so the width of the width is kind of determined by the variance parameter. Okay, so as you increase sigma squared, what happens is that the normal distribution gets flatter and flatter, and in the extreme case, if you take sigma squared to be infinite, you basically just get a flat line, right? So you can see hopefully that the probabilities, so as you increase, actually before I say that, let's just also do the example where sigma squared becomes really, really small. Actually, let's say it becomes 0. So what does sigma squared equals 0 mean? It means that there's no variance, right? So in other words, it's just a distribution that's centered right here, right? It doesn't actually change at all. And for really small values of so this is for, like, say, sigma squared equals to 0.1. So for really small values of the variance, it becomes very, very concentrated around the mean. And the extreme case is when you have 0 variance, in which case there's basically no fluctuation around the mean. It just, the probability is just at the mean. And the other extreme is when the variance is infinite, in which case it's just a flat line, right? So what's happening is that as you increase the variance, the probabilities get more and more spread out, and the distribution becomes less and less concentrated, and the uncertainty becomes greater and greater, right? Because when you have a peak distribution, right, the area here is the probability, right? So when it's quite concentrated around the mean, it's telling us that it's quite the uncertainty is kind of less because it's always going to be close to the mean. But when you flatten out the normal distribution, you're basically saying that there's more and more uncertainty, more and more values are possible, right? When I look at this guy, it's more possible to see values very far out, away from the mean, okay? And that's basically the idea of the entropy. So, if this example is kind of difficult, don't worry too much about the math. This is just kind of a aside for those of you that are interested. But it is interesting just to understand this equation and the implication it has, and contrast it with the first example that we saw for the Bernoulli distribution. So in other words, for the Bernoulli case, Okay, we know that the probability mass function is p to the power of x, 1 minus p to the power of 1 minus x. And for the normal distribution, the density function is 1 over root 2 pi sigma squared. Okay, now for each of these cases, let's look at the Bernoulli case. For different choices of p, you get a different, you're kind of modeling something slightly different. And we're saying that when p is equal to a half, you kind of have the most random case, right? The most uncertain case. And similarly for the normal distribution, you can tweak the parameters. You can pick sigma squared and mu. But actually from our calculation, it said that mu doesn't actually matter as far as uncertainty goes. Uncertainty is fully captured by the variance, and when you make the variance very large, you get the most uncertain possible normal distribution. Okay, so that's basically the idea behind entropy. But as I mentioned, the way we'll be dealing with entropy is looking at entropy of samples. Okay, and if you look at a if we go back to this example with the two circles, if you have two samples where the spread of information is uniform, you should expect a higher entropy than the one here where it's less uniform. All right, so with that being said, we can actually just move on to a kind of a more concrete example, which you've seen in the lecture notes, hopefully, but I want to kind of reiterate. Okay, so what is the point of entropy? Well, we just saw that, the highest, well, it's actually, sorry, let me call it the worst case error is when the sample is kind of uniform. Right? We saw that in the previous question with the data being split into k classes. In other words, when it has the highest entropy. Right? So in a decision tree, let's say you're at this point in your sample, and I'm taking this example from the lecture notes. You have 29 positives and 35 negatives. So this is the split of the current sample. And you basically have to make a decision, right? So getting a new test point, you want to classify as positive or negative. Based on this information, the sample is quite uncertain because it's almost 50-50. So we expect a very high entropy. So the way decision trees work is by splitting this sample by looking at a particular attribute or feature. So in this example, we have an attribute called A1. And A1 can take on two values, true or false. And basically, in this subset of true, you end up with the split. Okay, but you also have another attribute, attribute 2. Again, if you split on that, you get this split, 18 positives and 33 negatives versus 11 positives and 2 minus 2 negatives. Okay, so the question is, okay, we kind of have this idea when a sample is uniform, we get the worst case behavior. So how do we build a decision tree? Well, let's say you've got this sample, you have two attributes, A1, A2. How do you actually pick an attribute over the other to do the split on? Well, the idea is that you look at the gain statistic. Okay, so this is the gain of the sample based on attribute A. So sample and attribute. And it's defined basically as the expression Let me write it out and explain what it means. Okay, so what does this actually mean? Well, if entropy is bad, then we want to look at the, so find the attribute that decreases entropy the most. And this is equivalent to saying finding the attribute that increases the information the most. Okay, so entropy and information are kind of like two sides of, are kind of opposites. So when you have high entropy, you have high uncertainty, you have low information, right? So if I look at this sample, this is kind of not very informative. Like I wouldn't be able to discriminate a new sample just by looking at this. But if I look at this subsample here, then there's kind of, because one class is dominating, I kind of get more information. So if I'm trying to build a decision tree, if a sample has attribute 1 equal to true, then my sample is ending up here. I have more certainty about which class it belongs to. In this case, the true class. Similarly here, if we end up here, then it's kind of, it's easier to make the prediction here based compared to the prediction up here, right? So the way we pick attributes is by looking at the current entropy. So the gain is equal to the current entropy, okay, minus the entropy minus the entropy of, entropy gained by splitting on attribute A. Okay, so that's kind of, I think the easiest way to understand this is to just look at the numbers. But hopefully it should be intuitive, right? Like we start off with some entropy, and we look at the entropy left over after we minus the entropy from the newly added attribute. Okay, so in other words, if attribute A has really high entropy, right? So if A has high entropy, right? Then that's kind of a bad thing, right? Then A is useless. So the gain is going to be the current entropy minus a high number, and that's going to be close to 0, right? So in other words, if the entropy of A1, right, is also very high, meaning that there's also a lot of uncertainty in that attribute, then minusing a high number should give us a low number overall, and the gain is going to be quite low. However, if the entropy, so if we split on that attribute and that attribute gives us good discrimination, then that attribute is going to have low entropy. So when I do current entropy minus the entropy gained, then this should still be a high number, right? So if the second number is low, then the overall number is going to be high, and the gain is going to be high. Okay, so let's look at, well, for this particular example, okay, so A1, the sample gets split up into 2, so 21 plus 5 minus, 8 plus 30 minus, and the original sample is 29 plus 35 minus. Okay, so first things first, let's find the entropy of the original sample. Well, the split here is 25-35. So the probability of being in the proportion, sorry, of being in the first class, the positive class, is 29 over 29 plus 35, which is 64 log of that proportion, minus the proportion in the other class, so 35 over 64 log 35 over 64, and that's equal to 0.9936. So you should kind of, you should be expecting this to be quite a high number. And sorry, by the way, I want to make this really clear. So before I looked at the entropy of the Bernoulli, right? So we're effectively kind of doing the same thing here, right? Because you have two classes, so it's like a Bernoulli distribution. And then I looked at the entropy h of x, and it looked like this. Okay. And we saw the peak at a half. So just to make it really clear, when I plotted it over here, okay, this logarithm here is log base e, so the peak was happening at a value of around 0.27 or something like that. Okay, but if I took the if I plotted it for the log base 2, right, then hopefully you know that log base 2 of 2 is just equal to 1, right? So the peak would actually be at 1. The peak happens at the same point, right? It doesn't matter what kind of logarithm you use, the peak is still going to happen at the same point, but the value of the peak is going to be different depending on the log. So here, if we're dealing with log base 2, you can see that the entropy is 0.9936. It's extremely close to the maximum possible value, right? It's like here, 0.99. And the reason is the sample is has really high entropy. In other words, like it's almost equally split. So there's very little discrimination between the two classes at this particular point. Okay, so it's good to kind of try to interpret these numbers and see if they make sense as you're going. Okay, so now we have our entropy of S. Let's compute the entropy of, well, this is attribute A1, and I'm going to just call it A10. And what I mean by this notation is that this is S, and this here is A10 in the sense that this is the subsample or subpopulation when I split on A1 for the first for the first value of A1, so A10. So here I'm looking at the entropy of this distribution, and it's going to be hopefully pretty straightforward. It's 21 over 26 log 21 over 26 minus 5 over 26. Okay, and this gives us 0.7063. And again, I'm going to do the split for the second value of A1. So this population here, 838. Okay, so this is the entropy. I'm going to use this notation to mean the entropy, so I don't have to write it out each time. And this is just 0.7425. Okay, so then the gain for A1, well, it's the original entropy that we started off with, 0.9936 minus, okay, so if we're looking at attribute A1, let me just go back. We need to sum over all possible values of A, the attribute. Here we only have two values, so there's going to be a sum of two quantities. Within each quantity, we don't just look at the entropy at each subpopulation or subtree. We look at we weight it by the number of points in that particular kind of subpopulation. Okay, so this notation bar SV is the number of samples that fall into the region that you're looking at. So for example, here, for the value, for the first value of A1, we end up here. How many samples are here? Well, there's a total of 26. And from the original sample, there's 64. So the number here should be 26 over 64 multiplied by the entropy within this subsample. And the reason we do that is because you want to try to give higher weights, right? So if you have a split, if you have your split S and you end up, so let's say there's 100 points here, and then you end up with 100 points here and 0 points here. Well, sorry, if you end up with, let's say, like 5 points here, then the gain from this attribute should really, weight this, what happens here, much more highly, right? Because you've got much more data in that particular value, right? So in other words, if this is like 5 plus 0 minus, then this looks great because you have perfect separation, right? So the entropy is going to be minimized here. But if this 100 is split into 50 plus 50 minus, then this is maximum entropy. So this is going to be, a pretty bad attribute. And if we weight both of these equally, right, you're going to get a false, you're not going to get a kind of an accurate depiction of the usefulness of the attribute for the particular model. So that's why we kind of weight by the number of points that end up there. So in this example, for the first value, right, SA10, so let me just write it out so it's really clear, times the entropy there, minus SA11 over S times 7425, and this is equal to, so I don't want to write out the whole thing again, but this number here is just 26, this number here is just 38, right, the number of points in either class, and this number here is just 64, which is the total sample, and the entropy terms are just what we calculated up there. Here you get a gain of, let me see, it's 0.2658. Okay, so in other words, the reduction in entropy that you get by splitting on this attribute is we're going from like we're going from an entropy of almost 1 to an entropy of 0.26 or 0.27. So adding this attribute seems to actually give us a lot more. Seems to give us some improvement, right? So this is how much we would gain, how much information we would gain by adding attribute A1. If you look at the gain from A2, I'm not going to do it explicitly, but you'll just get 0.1643. So in this particular decision, if you're trying to build your tree, at each step of the process, you ask yourself, okay, should I add attribute A1 or attribute A2? You would compute the gain for each of the attributes and pick the one with the higher gain. Okay, so in this case, we would pick A1. So our tree, you'd start off with here, then you would look at A1 equals to true, A1 equals to false. Okay, now at this point, you would start the process again, right? You would look at if your attributes are A1 to AK, for each of them, you would look at the gain of splitting at this point for each of them, and then keep building your tree like that. Once the gain becomes a really small number, you might have a stopping rule in the sense that once the gain is below a certain threshold, you can kind of just stop. There's not much use in adding more and more attributes. Okay, so how do we build a decision tree? You start off with no decisions. Let's say that there's a split 50 plus, 50 minus. And then you look at your attributes A1 to AK. you find the gain of each one, and then you pick one. And by the way, this doesn't have to be a binary thing. It could be, you could have multiple, you could have a three-valued attribute or a four-valued attribute, whatever. You just compute the gain for each one. You'd pick that one, and then you'd start over again at each leaf, look at all the attributes remaining, pick a new node, and keep going until you kind of hit your threshold, and it's no longer useful to keep adding more and more attributes. Okay, so that's kind of the basic idea behind this algorithm. This is called the ID3 algorithm. So it's just one approach to building trees, but it's kind of the one that we'll focus on most in this course. And it's quite intuitive as long as you kind of understand this idea behind entropy. Okay, so this was just the example from the lectures. I just want to go through it again because it's a good thing to keep in mind. But let's look at the actual tutorial questions. This is question 2 in the tutorial, and we're basically given this data set. So in this data set, this is the y value, and these are the attributes. Okay, so this is our x. So the idea is, just kind of what I was saying earlier. The idea is we want to be able to choose an attribute to add to our tree. Okay, so we're basically at the leaf, and we're trying to figure out which of these attributes to add. So the point of this question is to kind of look at this intuitively, and then work through the numbers and see if the intuition works out. So just by looking at this, right, if you look at species, it looks like a pretty terrible attribute. And the reason is we have pearl, bismuth, garnet, amethyst, diamond, and jasper. Is that all of them? Right. So we have 6 values. So this is 12. This is 12 a data set with 12 values, 12 observations, and for the species attribute, you have 6 possible values. So that's kind of like, that's not a great thing to have, because it's really not enough data points to be able to do much with this information. The other thing is that the split, so if you look at Perl, for example, you've got 2 values of Perl for the no category, right? And you've got 1 of them for the yes category. So in other words, you have a split of 2 to 1 between the 2 classes for that particular feature value. For bismuth, you've only got 1 value, it comes up as no. For Perl, it's an equal split, right? 1-1 across the 2 classes. So you're really not getting much information at all from this attribute. But it turns out that, well, if we look at, say, Rebel, right? Then Rebel, it looks like, whenever Rebel is no, right? It seems to predict the yes class perfectly, right? So it looks like generally when Rebel is equal to yes, right? Yes, 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 yes. It seems to predict the homeworld should be no, and when it's equal to no, it seems to predict that homeworld is yes. So it looks like Rebel should be a much better attribute to split on. So let's actually just work through the numbers. So first of all, for species, we have 6 values. 6 values. And let me just write it out. So species, we have Perl, we have bismuth, garnet, amethyst, AM, diamonds, and finally Jasper. And, I mean, this is pretty painful to write out, but I think it's a pretty good example because we've only been looking at kind of binary valued attributes up till now. Now, if you look at Perl, right? Perl, we have 3 examples, 1, 2, and 3. 2 of them are in the no class, and 1 of them is in the yes class. So we have 1 positive, 2 negative. For bismuth, you have 0 positive, 1 negative. For garnet, you have 0 positive, 2 negative. And similarly for amethyst. So let me just do them all. Okay. So this is basically the same tree that we drew earlier. So if you look at, this, I'm just repeating this analysis here for this problem. So let's actually just look at the gain that we would get. Let's look at the entropy. Actually, it might be easier just to do it directly under here. So let's look at the entropy here. Let me call this HS. So H, the entropy of the species attribute for value P, Perl. Well, hopefully, this is pretty obvious. Negative 1 over 3 log 1 over 3 minus 2 over 3 log 2 over 3. This is going to give us a value of 0.9182. This is HSB. There is no entropy here, right? Because you have perfect separation. So the entropy here is 0. And similarly here, right, you also have perfect separation. So HSA is also equal to 0, and HSJ is equal to 0. So whenever you have 0, like whenever you have a perfect split, you're going to get 0 entropy. There's 0 uncertainty. And similarly for HSG. And finally from amethyst, this is going to have the same entropy as the Perl class. So this is going to be HS. This was HSD. HSA is 0.9182. Okay, so actually, let me look at the gain. We don't need this. Okay, so when we're computing gain, we need to look at the entropy of the sample. So let's look at the entropy of home world. Okay, well, home world, if we just look at this class, well, we have 7 nodes and 5 yeses. So this is going to be the entropy. It's going to be negative 7 over 12 log 7 over 12 minus 5 over 12 log 5 over 12. And that's going to give us 0.9798. So this is the entropy of the sample just before we do any kind of splitting. Okay, and then we want to look at the gain of home world when we add the attribute species. Okay, well, that's going to be the entropy of home world minus, well, remember how this works, right? We sum over all the values of the attribute and we weight them by the number of points that fall on that particular value. So here we have 3 points. There's a total of 12 points. So the first value is going to be minus 3 over 12 times the entropy here, right? Then you're going to look at this value. So here you're going to have only 1 point out of 12, and it's going to get an entropy of 0. So this term actually is just going to be 0. And same thing with this term. Then we get this guy again. So again, 3 over 12, 0.9182, minus 0, minus 0. And if you plug this into a calculator, you'll just get 0.5206. Okay, so the gain from adding species is just 0.5206. What about the gain from the attribute that looks better, right? Rebel looks better. Well, I mean, you should be able to do this, but I just want to do it. I just want to make sure it's 100% clear. Rebel takes 2 values, yes and no. And here it's 0 positive, 5 negative, and sorry, I think I switched them around. So when rebel is no, then we get 5 positive and 0 negative, right? Because when rebel is equal to no, we just get yeses. And when rebel is yes, then we get oh, no, I didn't switch them around. Okay, so, sorry, when rebel is yes, we just get no values. So 0 positive, 5 negative. And when rebel is no, then we get 5 positive and 2 negative. Sorry, so I may have made a mistake when I was explaining this earlier when I circled the no's. What I meant to say is that whenever we get a yes here, we always get a no over here. But whenever we get a no, there is some noise here, right? So these no's end up in no. But anyways, if you look at this, this is the correct way to look at rebel. And if you look at the entropy here, I won't compute it, but if you look at the gain, you'll get 0.9798. Well, let's just go ahead and compute it. So it's 5 over 12 times the entropy. Well, the entropy here, right, if you have a 0, you just get 0 entropy. Minus 7 over 12 times the entropy in this region, which is the entropy of the vector 5, 2. And so this number ends up being 0.4763. Okay, which is less than the gain from species, which is kind of unintuitive because we can just eyeball it and see that rebel is a much better attribute for predicting homeworld than species is, right? Species is almost useless because you know, most of the attributes just fall into a class of 1 point or 2 points. So what's happening is basically that the gain statistic, so gain SA prefers, well, it basically, yeah, so it prefers attributes with many values. So if you just look at if you look at Y, right? Well, if you have a lot of values, then what ends up happening is that the number of points that can fall in each bin is quite small. So you're very likely to get these really low entropy regions, which is exactly what happens here, right? We get 0 entropy here, 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 and here. And it's kind of to be expected because if you have 12 data points and 6 possible classes, then there's really not enough data points to be going into all the classes. So a lot of them are going to have very low entropy just by that fact alone. and not because species is a really good attribute. So we end up getting this really, I guess, pathological behavior because it's kind of preferring an attribute purely because it has more values. So the gain is not a great metric when you're comparing attributes with different number of possible values. So this takes us to the to consider something slightly different called the gain ratio. Okay, and basically it's just defined as the gain divided by the something called the split information. Okay, and so what the split, I mean, you can just think of it as a normalization to be able to compare different attributes with differing number of values. Okay, so how do we define the split information? Let me just call it SI, SA. This is just basically defined as the sum okay, and hopefully you should just see that this is literally just the entropy, right? You know, the fraction of the values in the ith value. So here C is equal to the number of values that attribute A can take, right? So we're just looking at the proportion that fall into the ith category as a proportion of the total sample and just computing this sum. And this is basically just the entropy, right? Minus P log P. Well, P is just the proportion in each class. So if we look at the split information for species, sorry, I should call this H for homeworld. Then what do you get? You get minus. So the first class, sorry, the first value had 3 points here. So minus 3 over 12 log 3 over 12. And if you keep doing this, you get minus 1 over 12 log 1 over 12 minus 2 over 12. Okay, and hopefully you get the picture. I'm just doing this for all possible values. So there should be 6 terms in the summation. And this gives me equals to 2.4591. And if you look at the split information for Rebel, okay, well that's just going to be minus 5 over 12 log 5 over 12 minus 7 over 12 log 7 over 12, and this is 0.9799. So now when I look at the gain ratio of species, well, that's the gain that we got. So we computed that in the previous slide, so that was 0.5206 divided by the split information, so 2.4591, and this gives us a value of 0.2117. And the gain ratio for Rebel is equal to 0.4763 over 0.9799, which is 0.4861. Okay, so when I said this is a normalization, hopefully you can see that because you know, the normalization here is almost 1, right? You know, the gain ratio and the gain are almost equivalent, whereas here there's a significant change. And basically the normalization is just accounting for the fact that the gain prefers attributes with many values, so we want to just control for that. Okay, so under this new ratio, hopefully you can see that we're actually picking the attribute that kind of made the most sense in this particular example up here. Okay, So when you have attributes with multiple values, it makes more sense to consider the gained ratio rather than just purely the gain. Okay, and I guess before we finish up, the last section is, so we've been talking about decision trees. Basically, all I've mentioned is classification trees. But decision trees can also mean, can also be used for regression. Okay, and so that might kind of seem kind of weird when you first hear it, because you know, you need to make an if-else kind of decision. How do you do that for a continuous data set? Well, let me just kind of illustrate what happens. So let's imagine that let's imagine a regression problem. Let me just call it feature X. So this is a one-dimensional problem, and here's your Y. So let's say that you have some kind of data that looks like this. And maybe let's make it a bit more interesting. Okay, so let's say you had your data set that looks like this. So if you were just going to do a linear regression model, your regression would end up looking something like this. Okay, and it kind of misses basically all the groups, right? So when you fit a global model, when you have this kind of local structure in your data, you end up with quite a poor model that misses a lot of the aspects of the data. So one thing you might do is fit a regression tree. So what a regression tree does is basically it kind of looks at the attribute X, and it tries to find you know, it tries to split the input space into the best possible regions, right? So let's just not talk about how it does that yet. Let's just assume it knows how to do it. So if you consider this particular example, and you allowed it to split the space into 3 regions based on X, it would probably pick something like this. Okay, and then it would treat each region as kind of being its own thing. And the most simple, so let me use green for the simplest regression tree. What it would do is basically look at this region by itself, and it would fit a model for this region. The simplest regression tree is just the mean. In other words, the prediction for this region is just the green line, the mean of those points. For the second region, it would just predict this point. And for the third region, it would predict something like this. Okay, but it doesn't necessarily have to do the mean, right? So we could do a linear regression. Let me do that in purple. And basically, the idea is very similar to nearest neighbors regression. Basically, it's just going to build a linear regression. So we'll call this y1 equals to a1 plus b1 x. But it would only build them based on the points in this region, right? It wouldn't look at the other points. Similarly, here it would get something. It would get a regression that looks like this, and maybe something that looks like this over here. Okay. In each region, it would get a different. It would get a different model. And you're not restricted to regression trees. So there's actually something called a model tree, where in each region, you could fit something really complicated. So let's just call it advanced model, you could kind of picture fitting something crazy in each section. It doesn't really matter, okay? But the idea is that this is how you'd use it for regression. So the tree kind of aspect of it is how do we split the input space into regions and then try to do the modeling on the actual region. And if you look back at the initial example that we talked about, right? The idea is that this is the original region, right? It's really hard to do classification on the original region. How do we split the input space and get a better, get an easier space to do classification on, right? So when we split on this attribute A1, we fall into two regions which are kind of easier to work with than the original region. And that's basically exactly what's happening here. You know, taken as a global function, this is a really hard thing to learn. But if you look at each region by itself, it's actually it's a lot easier. It's a much simpler problem. Okay, so basically, let me kind of extend this to a two-dimensional. So imagine you had features x1, x2. So this was just just a single feature model. But you can imagine if you had two features x1, x2, and some y value, what the regression tree is doing is actually finding. So I'm taking this example from Elements of Statistical Learning. Basically, you're trying to find values t1, maybe t2. Okay, and maybe you know, T3 over here. And you're basically trying to partition the space into regions, R1, R2, R3, R4. You might have something like this, R5, R6, R7, where this is some T4 value. And on each region, you're building a particular model, right? So your tree would look something like this. You know, if x1 is less than t1, then you, sorry, let me make this a bit neater. Okay, so if x1 is less than t1, or if x1 is greater than t1, so t1 is here. If x1 is less than t1, then we need to test for x2 being less than or equal to t3, or greater than or equal to t3. And basically, if you were in this region, then this is region R2, and this is region R1, and you would have fit some model here. So y hat 1 is equal to whatever your model is, and you would fit some different model in this region. And so this is how the regression tree works. You still put your example down the tree, find the region that you fall into, and then use the model that you fit to that region. Okay, so that's basically what I've done up here as well in the one-dimensional example, but basically it works for any dimension. Okay, so at this point, the only remaining question is how to, you know, so it's pretty straightforward to be able to build the model in each region. The only really thing that we haven't mentioned is how do we actually find, you know, where to split the input space and, you know, actually identify these regions. So I'm just going to show a simple example of this. So let's go back to the one-dimensional example, and I mean the same intuition is going to work for multiple dimensions, but it's much easier to see it here. So let's imagine that we have a similar data set to before, and basically the way it usually works is we look for a binary split of the attribute, right? And the reason this works is if you go back to this picture that I drew here, first we look along x1 and x2. We identify the best split point, say T1. Okay. Once you identify T1, okay, then you again look at, now you have two regions. So actually, let's look at time 0. We have our x1, x2. Now there's no splits yet, right? At the first time point, we scan across x1 to find the best split point, scan across x2, compare them somehow. So this is just like looking at the gain ratio in the classification sense, except that we need to use a slightly different procedure. But we basically just pick one of the features that gives us the best performance, and within that feature, we've identified a split point, say T1 for x1. And now we're left with region 1 and region 2, right? I don't want to call them region 1 and region 2 because I've used R here, but let's just say C1, C2. Okay. Now at time 2, so you could stop here, right? You could build a model in each section and just finish there. But you could say, oh, maybe the data could be split further. And so you might, scan again and identify that splitting on x1 at T2 is the best option. I should draw it below here. So you end up splitting the space T1, T2. But at the same time, so say this is for region 2, gets split into two regions, C21, C22. But for region 1, C1, it turns out that it's actually better to split along x2 at T3. And so, let me just draw it. Let me draw a really big diagram. So we split C2 into C21 and C22 based on T2 and T3, sorry, T1 and T2. And then we split C1 into two regions, C11, C12, right? So you're carrying out the split procedure on both of the regions at each point. Now at this point, you might further look at each region and try to split each region, and build a submodel in each region. Okay, in this case here, right? How do we actually identify a split region? Well, we need to actually figure out a location that kind of, if I just eyeball it, it's obviously here, right? But how do we actually quantify that? Well, there's many ways to do this, but one way to do it is to define for any combination, for any JS, we define the two regions R1 JS and R2 JS. Okay, let me actually just define what these things are. It's the set of points such that the xj is less than x and xj is greater than x. So in other words, I have my data points, right, my sample, and I want to basically split them into two regions, R1JS, R2JS. S is the actual split point. It's the actual location. So it's actually the split is going to happen at S, and X such that xj is less than or equal to S is just all points in my data set that are less than this particular point, and otherwise these are the points greater than that split point S. Okay, and then let's try to write a minimization or optimization problem that kind of captures what we want to do. Well, one way to do this is to pick the split to minimize the variance. Okay. So what does that mean? That means that, there's obviously a variance for these data points, and we want to basically pick the split such that the variance, well, so let me actually just write out the optimization. So actually, let me write out the whole thing, and then I'll explain it once it's. Okay, so I mean, this thing looks really scary, but it's actually really simple and intuitive once you look at the picture. So basically, if we look at this optimization problem, okay, we're basically splitting the data into two portions, into R1 and R2, and within each group, we're computing this quantity here, right? This is the we're finding the C that minimizes the sum of squares, okay? And we're doing that for both regions. And then basically the value overall is the variance across the two groups. Okay, so this is the variance group 1, variance group 2, and the groups are dependent on J and S, and we're trying to find the J and S that give us the smallest possible variance. Okay, so in other words, we want to basically find a split point such that group 1, the variance of group 1 plus the variance of group 2 is as small as possible. Now this looks kind of complicated, but if you really think about it, okay, let's actually just compute. So let me actually just show you this optimization problem. Let's say I just have n data points, and I'm trying to compute the value m that minimizes this value here. Okay, so this is just a function of m. So how do I minimize this? Well, I just take derivatives. Okay, so how do I differentiate this thing? Hopefully you recall from the first tutorial that all you're going to get is the okay, very similar to the least squares derivation, and we're going to set it equal to 0, right, to minimize. And then you can show that you can get rid of the -2. You can move the m to the other side. And basically this shows us that m hat is equal to 1 over n yi, the sum of the yi's. So what I'm saying here is that if you're trying to minimize the sum of squares, the minimizer is the mean. So another way of thinking about the average value is it's the value that minimizes the sum of squares from that point. Okay, so let's go back to this expression here. This is basically the variance of group 1, the variance of group 2. The C1 value is just going to be the average in that group, and the C2 value is going to be the average in this group. So this is actually computationally very simple to do. So all we do is say you have, let me just picture it like this, our data points x11, x12, x13, all the way up to x1, let's say 10. Let's say we have 10 data points. Okay. To do this minimization, okay, we're going to pick to split. The first split is going to be here. So we're going to have R1 just being the set x11, and the second group is going to be R2, and that's going to be x12 all the way to x110. Then I'm going to compute the variance in this group and the variance in this group and add them together and get a number. Let's call it V1. Then in the second stage, I'm going to look at, so this is the first step, so time 1. Then at time 2, I'm going to look at x11, x12, and then the second group is going to be x13 to x110. And I'm going to get another number v2, and I'm going to continue this until I basically cycle through all possible groups. And at each stage, right, computing this actual value here is quite simple because all I need to do is compute the average of the values in each group and compute the sum, okay? So hopefully, let's just look at the visual depiction, right? So in the first step, I'm going to isolate this guy and then put these guys in a group. Now, you should hopefully see that the variance for the second group is going to be massive because the mean in the second group is going to be somewhere here. So the squared errors from the mean are going to be very large, and so V1 will be quite bad. Similarly, when I look at x1, x2, so when I look at the second time point of the algorithm, I'm going to combine these guys. I'm going to get the same problem, right? I'm going to get a very high variance in the second group. So the algorithm keeps going until I get to the point where I basically isolate these groups, right? Now the variance in each group is going to be quite small because the average now for this group is here, and the average for this group is here. So the variance is going to be quite small relative to what we had before. Okay, and then the algorithm is going to cycle again, and we're going to get this group versus this group, which is going to have a very high variance, et cetera, et cetera. So the algorithm, the way I've kind of defined it here, will identify this as the xj, right, and the value s to be here, which cuts the space up. Okay. Now, if you have multiple attributes, you would repeat this kind of process for each attribute, and you would look for the attribute with the lowest overall variance, and you'd pick that one. The only problem is that if you have attributes that have different scales, so for example here I'm looking at the variance of x1, like, you know, if x1 is on a scale, x1 is between 0.001 to 0.002, and my second attribute is, you know, on a scale of 1 to 100, you need to be careful when you compare the variances, right? From this process, because, you know, for example, you'll always pick x2 if you don't scale it, because the values are just going to be naturally larger. So you need to make sure you scale your data before you actually compare variances across groups. Okay, but this is kind of the way to split the data. Okay, and once you split the data, right, once I've identified this split, it's really simple to fit a model in each region, right? Just using our basic, you know, linear regression tools or whatever you'd like to use. Okay, so hopefully that's pretty clear. This picture is nice to keep in your mind, and, you know, combining it with this tree, you know, the tree part is actually splitting the space, and then at each leaf we can just do whatever we want, and whatever we want could be fitting a brand new model or just taking the mean as the predicted value. So one thing we should kind of mention is if you kind of recall the way I was describing this process in time, you first break the space into 2, then you break it into 4. Each time you're getting kind of smaller and smaller regions. And so what could potentially happen is that, so if you look at, you know, you might have 100 data points, and then after one split, you might split into 2, you might get 20, 80, and then let's say you split again. Okay, so the point I'm trying to make is that at each split, you're ending up with less and less data in each region. Now, if you think about what I'm doing here, right, I've got 5 data points, and then I'm going to try to fit a linear regression in this section, right? I mean, that's, you know, I'm building a regression of x1, x2. So what could end up happening, and you know, this example is just, you know, still 40 is not too bad. You know, you can imagine that you end up with really small regions, potentially, where you have like 2 data points or 1 data point. So one way to avoid that is to do pruning. Another way to get around this problem and have more reliable estimates is called smoothing. So this is really, I mean, the idea is kind of similar to naive Bayes. You know, we end up with problems when we just use the probabilities calculated kind of immediately. So one way to fix this problem of low sample size for regression trees is to actually so the way it would work is instead of just fitting models at the leaf nodes, right? So what's happening here in this picture, right? You're looking at x1 less than t1, x1 greater than t1, and then you're looking at, you know, x1, you know, less than t2, x1 greater than t2, and here you're looking at x2 greater than t3, you know, whatever you're doing. Once you get to the leaves, you have your data points, and then you're fitting a linear regression. So instead of just fitting models at the leaves, right, this is a leaf and we're fitting the model at the leaf, what you could do is kind of fit models as you go, right? So I could fit a global model. Let me use a different color, right? When I have my 100 data points, I could fit a global model. Actually, maybe there's a better picture. The one-dimensional case. Okay, so let's say you have some weird example like this. So before we do any splitting, right, you could fit one global model. Okay. Then you would split for the first time, and say you split maybe like this. And then you would fit models in the split. So maybe like this, and in this region you would fit the blue. Okay, so what I'm doing here is basically, I've got 2 regions now. I'm fitting a blue model in this region and a blue model in this region. And then I might split again. I might split here. And again, I would fit, you know, in this region, maybe I'd fit this model. And in this region, I'd fit this model. And so what I'm trying to explain is that we have a global model. Then we have kind of a more local model. And each time you do a split, you're getting kind of a model based on a smaller subregion, you know, a smaller number of samples, but a smaller area in the input space. And so what we can do is, when you're doing the prediction for the really small region, is to try to use the information from the previous predictions to kind of smooth your estimate. Okay, so let's look at the smoothing example. So from the notes, let me just write out the formula and then explain how this gets used. Okay, so this is kind of our, you can think of this P prime as our smooth probability. Okay, and then we can define P prime as our, well, let me write down the actual definition. So it's the prediction passed up to next higher node. And then P is the prediction passed up from node below. Q is the value predicted at the current node. n is the number of data points that reach node below. And k is just a smoothing constant. And basically, the higher that k is, it's going to have a different smoothing effect, and we'll see that explicitly in a moment. Okay, so I think the best way to understand this, because it's a lot of terminology, is just to look at a kind of an example. So here's an example that I just kind of made up. Hopefully it helps. It's so let's just imagine that you know, at this, you start off with 100 data points, and then you have a different feature, say feature B, in this region, right? This is a different. So when I say A and B, I mean different regions that we've broken up the space into. So, for example, this is A. This could be region B. You know, and so I'm just kind of trying to simplify things. So the tree is taking us to different regions. In this region, we have say 20 data points. And then, you know, this region gets split up again. And let's say here we're at C, and here we have 10 data points, and then C gets split up. And finally, we have D with 5 data points. I think that should be enough. Now, what I was saying is that in the original or non-smoothed tree, you know, let's say let's give these guys names. So let's say I have a new value x star. I want to predict it. I put it to my tree. It happens that it goes down this path, and so it ends up in this region. And if you look at this region, you know, I've gone right, left, right. So let's just say this is called P010. What I mean by 010 is right, left, right. So this would be P011, for example. This would be P01. This would be P0. In my original non-smooth tree, right, I just get to the subregion. I build a model at the leaf, and I get prediction P010, and that's what I return, right? So this is my returned value. Now, the problem with this particular probability is that it's based on just a sample of 5 points. And so you could get very high variance in your estimates because, you know, in small subregions, you can get, you know, very different behavior to the global region. So smoothing is a way of kind of, you know, smoothing out your estimates, or in other words, reducing the variance in the estimates. So we don't want the estimate in the subregion to be very different. So for example, if the predicted value in the C region is extremely different to the predicted value in the D region, you'd kind of be a bit worried because, you know, so if we look at the previous picture, let's say this is our, let's say this is our region D, and then this is our region C. So we kind of want the change in prediction from region C to region D to be not too great, right? If the prediction for a particular value in region C is like 100, and then it's like negative 1,000 in region D, then you get this really high variance in your estimates. So you want the, as you're breaking the region into smaller subregions, you want some smoothness across the estimates, across the predictions. Okay, so this is the non-smooth estimate. So now let's look at the smooth estimate. And to compute the smooth estimate, we're going to basically use this formula. And this formula is recursive. And what I mean by that is we're going to compute a value that basically gets passed up the tree till we get a final smooth value. All right, so let me just pick arbitrarily k equals to 2. It doesn't really matter for now. I'm just picking a random value, k equals 2. And I want to compute the smooth prediction at D. So if you look at np plus 2q over n plus 2, okay, so n is the number of data points that reach the node below. So the node below D, right? There is no node below D, so we just get 0. Similarly, the P is the probability, the prediction that's passed up from the node below. Well, there is no node below, so that's also 0. Plus 2 times Q. Q is the value predicted at the current node. So the current node predicts 0, 1, 0. And we divide by n plus 2, so 0 plus 2. So we get P0, 1, 0. Okay, which is pretty straightforward. The smooth estimate at D is just the prediction at D, right? There's nothing to smooth, there's nothing below. Then we go up to the next node in the chain, which is C, and we want to look at the smooth probability at C. Now it's NP plus 2Q over n plus 2. Now, n is the number of data points that reach node below. Well, the node below C is D, and there's 5 data points there. P here now is the prediction that gets passed up from the node below. So it's P0, 1, 0. And maybe it's better to just write P prime D just to make it explicit that this is the smooth prediction, right? That comes up from below. Plus 2 times the prediction at the current node, so I called that P0, 1, right? That's this guy. Divided by 5 plus 2. So if I write this out, I'm going to get 5 over 7 P prime D is just P0, 1, 0 plus 2 over 7 P0, 1. So what you should notice here is that the smooth prediction at node C is a linear combination of the prediction at C, right, from the submodel at C, and the prediction at the submodel at D. The weight that we give the lowest model of the leaf is the highest weight, but we smooth it by kind of still incorporating information from the previous model. Okay, let's go up one more step in the tree. And now we look at, well, n is going to be 20 now. Sorry, n is going to be 10 now. It's the number of points in the leaf below, times the prediction that gets passed up. Well, the prediction is not P0, 1, right? Be careful. It's P prime C plus 2 times Q. Well, the prediction at the current node is P0 over n plus k, so 10 plus 2. Now, if you actually take this term, which is P prime C, and you plug it into here, and you kind of simplify things a little bit, what you'll get is that this is equal to 25 over 42 P0, 10 plus 10 over 42 P0, 1 plus 7 over 42 P0. So as you keep going up the tree, you're incorporating the previous models into your estimate. But the model is always going to give the highest weight to the leaf model. But this is going to be a smoother estimate in the sense that it's not, if the prediction is incorporating the previous models, then it can't be too different from the previous models either. So the variance kind of drops. The weight that we give each submodel is based on the number of data points and the smoothing parameter k. So as you increase k, you should see that the weight given to the previous models is going to be lower. Okay. Now the final prediction is P prime A. I'm not going to do that explicitly. You can compute it, but you will basically get a weighted prediction based on all the models, and you would have some global model here, P star, and that would be your final estimate. So hopefully this is quite intuitive, and in the tutorial there's a question on smoothing that I'm not going to cover. I want to leave it for you to kind of figure out, but hopefully this example kind of illustrates what's going on when we do smoothing for trees.